Okay, I just wanted to give you a quick tour of the modular noise synth I've been building. I think I may be putting together a couple more modules, like more of the same, but it's pretty much done for now. I need to mount it in something. Everything's still just on boards, kind of separate. But yeah, it's done. I think by the time this has gone up, I'll have already posted a video of me playing with it. Um, it's very noisy. It's kind of cool. It's a lot of fun. I've learned a lot doing it. Um, so the first thing is I just wanted to go through a few kind of general things about it. Um, Kind of things that I've learned and things that I had to do. So what happened is I did the first video about the shift register module, because my original idea was that I was gonna record me putting them all together, and then put videos up for each one and just do the whole process. Um, I have now put so many hours into getting this thing working. I can't even tell you. I have seen some shit, and I very quickly realised that first one was kind of a fluke. It just worked and worked perfectly. And that first video, it genuinely was first time, finished it, worked perfectly, and I was so happy. Um, all the modules since then required messing around. I screwed stuff up. It turned into such a long, drawn out process. I thought no one wants to watch me soldering for like 2 solid days, and putting the multimeter on stuff. And well, maybe some people do want that. There's other people who do that kind of stuff better than I can, and frankly, I was getting frustrated, and you would have just had hours of me sat in sullen silence staring at components. And I'm saving that for my next art piece, so I didn't want to waste it here. Um, so yeah, so what I decided to do was just make the damn thing and then come back afterwards and talk about the process. Um, so there's a few things that happened. So after that video, once I started getting some modules together, I realised that power needed sorting. So it all runs off a single 9 volt kind of wall wart power supply, which is cool. But actually getting the power to the individual modules, if I just grab one, because I've done all the power's just on header pins, so right there, and I kind of like I've used right angle header pins, so you can just sort your power however you want. With the plan being that I was going to use, I only have a loose one, these DuPont connectors, these little things that they have a hole in the end, and that just kind of goes onto your header pin, and at the other end you get your wire, you strip a bit off the end, you have this little metal housing that you crimp onto the end of the wire, and then you push it into there, and it's a real faff, it's a pain, and I hate doing it because I keep screwing it up. It's small, it's fiddly, and I don't have the patience for that. So what I ended up doing is I looked into other alternative connectors and settled on MTA 100, which looks like, I should have prepared this, which looks like this. So I'm not sure how close I'm going to be able to get and you still see what's happening, but basically your wire, you just cut your wire, you kind of rest it on the top of this thing like so, and then use a tool to push it down, basically punch it down, and there's some little metal things in there that cut into the wire, make your electrical connection, a little plastic bit that grips it, keeps it in, and it's quick and it's easy, saves messing around. So I bought a load of those connectors. I bought a load of the header pins that go with them because it's the same pitch as the header pins I was using. So I've not had to redo the ones that I've got. But on future boards, I'm going to try and use the proper header pins because it'll lock on, so it won't just accidentally come off. And I also bought the tool to punch down as connectors. That's this thing. So it's got these little teeth on the end, and you kind of grab that and you punch it down. You don't literally punch it, obviously, although actually that might work. So this that fits in the palm of my hand was like nearly 30 quid. It's a piece of plastic with little metal teeth, but like I figured I'll get some decent use out of this. The individual connectors are really cheap, so I think it's going to be useful. It's going to make this kind of thing a lot easier in future, and it means that I won't shy away from using connectors, using wires where I need to. So once I had that, I made this thing up. So there's a load of MTA 100 connectors on some wire, and this is on a bit of strip board. So that this is the one where it's got the copper on the back, so like all these lines are connected together. So I just made a little kind of power bus, and then on one end I've just got my power socket there. So I'm going to plug my adapter into that, and then that'll power all the modules. Saves messing around. It's fine for my needs. I understand that as I start to do more complex stuff, this won't cut it, but it works for now. So you know, it's tested and it works. So that's good, but expensive. And oh no, there was something else I needed to tell you. Oh yeah, I've discovered that I've ended up wasting a few of my boards because I've messed stuff up. And these are ones that I'm not going to use because they're just not working. I kind of desoldering the components as I go along. I ended up speccing the wrong potentiometers on a bunch of stuff and having to put in another order of potentiometers. As stated before, potentiometers are like the most expensive thing you'll ever own. So that was a bit of a pain. And then I'm slightly disappointed kind of in myself in that I don't feel like any of these boards are good enough to sell yet. I think I can. I think there's scope for working them. Doing some revisions and working towards something that I can sell a few of. As like the idea is to have for it to be kind of cheap and dirty little modular system. I'm not there yet though. But my design goals, which I think I've stuck to pretty well, I wanted it to be cheap, kind of self-contained. I decided I'm not interested in worrying about interfacing with other more professional modular gear, because I don't have any, and baby steps. Well, they'll take things one step at a time, maybe in the future. The advantages of this, though, it means that I don't have to worry about how do other people do it. I don't need to know standards. As long as my stuff works with my stuff, then that's fine. So it's kind of freed me up to just not have to worry about that kind of thing. I decided I wasn't going to build stuff to go into a rack. Or a kind of some kind of rack-based system. My goal is to have some kind of like desktop big panel with everything on. So that's why everything is odd shapes and sizes, because I'm going to worry about the layout later. And I'm thinking I'm going to try and use the board layouts in Eagle, maybe export them somehow, get them into an image editing program, make some kind of layout from them and have it printed as a sticker. So maybe go on a piece of Perspex or something. Not that yet. So we'll see what happens. I think that's it. I think that's me general stuff. So I guess we should dive straight into looking at the individual modules. Okie dokie. So this one is a dual oscillator, as it says on that end. under those capacitors. Oops, it's under there. So yeah, dual oscillator. So basically, the idea of this one was to try and have two square wave oscillators with one, both controlled by the same pitch control, but with one of them having a kind of an pitch offset control, so you could so you can get a kind of beat in kind of sounds, and then also have a symmetry control for both. So that's kind of what I've got. So quick run through. So I guess start at this end. That's the symmetry control for oscillator 1. That's the symmetry control for oscillator 2. That's the pitch offset for oscillator 2. That is to turn oscillator 2 on and off. That's the master pitch. That is a pitch input. Basically, you can override this pitch control by plugging something into there. It's kind of voltage control. That's the output. Power on header pins there, and the LED's kind of in line with the output. So the LED, you can kind of see a representation of what it's doing. I don't think it'll pick it up very well in this video, but we'll see what happens. So things that went slightly wrong, as you can see, there's this massive resistor. So I ordered a 3-watt resistors instead of the quarter-watt resistors that I should have ordered. Just put my phone on silent like I should have done before I started, because I am a professional. Right, so yeah, that's 3-watt instead of quarter-watt. These ones are all quarter-watt. That's the kind of normal ones that I wanted for this size. I just wasn't paying attention when I ordered it. Luckily it's on the end there, so I could just kind of wedge it in like this. Obviously that's not ideal for future. The reason I used 5-watt is because this is in series with the hang on, let me figure this out. Basically, oscillator 1, the voltage that's controlling the pitch of oscillator 1 is going through this 5k resistor, and then this pot that's controlling the oscillator 2 offset is a 10k pot. So in theory, when this is at kind of the halfway point, it should be exactly the same pitch as the other oscillator, because this resistor is half of this potentiometer. Turns out 10k isn't quite enough for it to work how I wanted it to. I probably want like a 50k pot on there, and then a 25k resistor. So I've not actually looked if that's a more standard value for resistors. Hopefully it is, so I won't have to mess around with this nonsense. The other things that have happened are when the second oscillator is off, it still kind of interferes a little bit. I think it's something to do with the ground rail. I think there's, I think this this capacitor is supposed to kind of reduce the amount of noise. I think I've maybe not used the right value there, so I need to experiment with that a bit. And the other thing is, I've got 2 pairs of transistors. So each pair of these is controlling the pitch of one oscillator. They are not actually matched pairs. I've just put 2 transistors in there. So that means that when you're changing the symmetry of these oscillators, it's not it acts a bit strangely, and a pure square wave, you kind of in theory should just be at the halfway point, but it isn't. It's at different points on each one. I think because because it's not symmetrical, because the transistors are not matched. So yeah, so that's the stuff that's gone wrong with it. But so I guess we should have a listen to it. So that's not to say that it's all bad, because actually, I mean, it's kind of noisy and quite nasty, but if you like that kind of thing, and I happen to like that kind of thing, then it's alright. So, I'll put some power on there. So, I mean, you probably can't see. I can see that LED is flickering to show what the output's doing. You can maybe pick up on that a bit. Let's see what happens. So yeah. So that's with both oscillators switched on, actually. So the second oscillator kind of doesn't get far enough away from the first one in pitch. I suppose I should try and make these vaguely square. So if I switch it over to just one oscillator, you can kind of hear it's a bit noisy, and it still does stuff when I change the second oscillator. So for the pitch input, I'm just going to hook up another module. So I've got some. Oh, that's interesting. When I plugged the power in on the other module, this one suddenly became a lot less noisy. Okay, to be continued. So I've got a single oscillator module, but I'm going to take the output from this module, just patch it into the input. So I've got it on a really low, low pitch, the controlling oscillator. So if I move the pitch of this controlling oscillator up, and obviously I can still mess with the symmetry of this one, put the other oscillator in. So you can get quite a range of sounds out of that. And to be honest, you can get quite a range of sounds out of this one just on its own. Which is kind of cool. So like I said before, it's noisy and nasty. But if you like that kind of thing, then you're golden. So I guess the next one to look at is the single oscillator board. So well, it's the same board, but I realised that just by kind of missing out some components, I could configure it as a single oscillator. And what I've done, yeah, I've got the right one. So I've sharpened on the back there, although it's rubbed off, the word pair. That is because for this one I actually bought matched pair transistors. And for this one, I don't have matched pair transistors. So maybe it's time for an A/B test. I've not actually done this yet. So the one closest to me, this one, is the one that isn't matched pairs. and the one furthest from me, which is this one, is the one that's matched pairs. But just as a quick run through, so basically I've just missed off this capacitor was unneeded, didn't need these transistors over here, didn't need these pots, didn't need these resistors, didn't need the switch, and it all works kind of hunky-dory. So yeah, so here's the paired one. Let's give it some power, and where's my output gone? So as you change the symmetry on this one, the pitch changes, but it seems to change the same amount in each direction. And I've had this on the oscilloscope, and the kind of proper symmetrical square wave isn't quite at halfway. So that's halfway. The square wave is actually about there. Now I think I could put like a little trim pot in series with this potentiometer, so you could calibrate this. I could probably do the same with the pitch, and maybe on a future revision that's what I'll do. So that's that one. So let's get the other one in. So this is the one without the pair. See what happens here. So again, it's an oscillator. I don't know about you, but to me, that first one sounded like a better. So the pitch changes a different amount in each direction, and it's not. You can tell that the kind of high and low points on the square are not getting shorter and longer at the same rate. I'll try and remember to get this on the scope and do this test again, and show you how it looks on the scope, and you'll be able to see what I mean on that one. I was just editing the video and I remembered that I said I would put this on the scope. So right, quick as I can, this is the paired one. So as I said, the proper square, well, I know it's a bit wonky on the top there, but the proper square is actually just above the halfway point, about there. Then as I go up, see the low ones lengthen out and the high ones kind of shorten. And then as I go back down past that point, the opposite happens. So I think if I did have like a trim pot, I could just set the center point, and that'd be okay. So right, I'm gonna very quickly. Oh my god! I'm gonna very quickly swap these over. So that was the paired one. So this is the unpaired one. See if I can get this one here. Just put the pitch up a bit. So that one, where do we reckon they're even? About there, no, there maybe. That's about 3/4 of the way up to the top. So then as I go up that way, that is as far as that one will go in that direction. But then the other way, it'll obviously go quite far because those transistors aren't paired. I guess just for fun, let's just shove some of the stuff on the scope since I've got it all set up. This is the shift register. Oh, too far. So that's, as you can see, it's just square waves, but they're kind of each time it goes around, it's getting different different values. You can kind of see the, in a way, you can kind of see the clock. I think that the kind of the width of the smallest bit there is probably how fast the clock's going. Oh, that's kind of cool. So yeah, there we go. Back to the rest of the video. But yeah, that's it. I mean, you know, this one's kind of pretty straightforward. I mean, I guess I can plug in the other one again and just patch them together. So again, the pitch input control just does the master pitch. So yeah, a lot of kind of again, frequency modulation, I guess. There, you get some really interesting tones just from two single oscillator devices. So, but that's it. I mean, you know, it's got two controls and a pitch input. That's what it does. So that's pretty straightforward. This one I've already done a video about, so I won't go into too much detail. Well, no, I'll go into detail. I won't dwell too much on how it sounds. So this is a shift register synth. So what you've got is 4 square wave oscillators, the pitch of which is controlled by these 4 pots across there. I've got different value timing capacitors on each one, so they've got a slightly different pitch range. And these are being fed into a shift register. So to imagine what's happening here, imagine that we're looking at it's kind of simple because it's square waves. So your value is either low or high. So square wave is just going from low to high to low to high to low to high, like it's really fast. That's a square wave. If we say start at this end, and this is a slight abstraction of what's happening, but if we start at this end and we check what value is this at, is it low or high, and whatever value that's at, that's what we set our input to. Then we move to this one and do the same thing. Then we move to this one and do the same thing. Then we move to this one, do the same thing, and then we go back to the beginning, and we just keep cycling around like that. That is what this does. But when you get back to this first one, maybe it was high the first time you checked it, but this time it might be low. You know, you don't know. Basically it's a function of this one controls the clock speed, so this is how fast is it moving along them. So it's, you know, how fast is this versus the rate of this oscillator. So it's sometimes when you get to it it'll be high, sometimes when you get to it it'll be low, and there is a pattern to it. You can hear that there's a pattern to it. It's not random, it's not noise. Well, it's noisy, but you know, it's not like white noise or anything. It is kind of slightly tonal. And actually what's happening is it's not that you're checking each one, you're loading all 4 values into a shift register. So you know, it's just a thing that'll store some values, and then you can move the values along. That's the shift part. The values move along, and once all 4 of them have been pushed to the output, it takes all of them again at the same time and then pushes them down. so the speed is how fast it's pushing them out. That's my kind of fairly poor description of what a shift register synth is doing. If you're interested in kind of getting into this stuff, have a read up of shift registers, because they're just kind of interesting from a computing digital electronics point of view. It's kind of interesting what they do. So we've got 3 chips. I've got 4006 for the oscillators. I got a 4017, which is the shift register. Is it? Or is that the timer? Oh, I can't remember. I've got a 4017 and a 4014. One of them's the shift register, and one of them is a counter. So the counter was needed just to make the shift register do its thing. And then the shift register is as described. So we've got an output here. We've got a clock input, so you can override. This is setting speed, but you can override it by putting a clock signal into there, which is basically any square wave signal, potentially any signal, although you might get weird results. Then these here are inputs, so you can override the oscillators. The 4 oscillators, each one can be overridden with its own input. So what happens at higher clock rates, you kind of just get a mix of all of the other signals coming through, and then as you reduce it, it's kind of like you're reducing the sample rate of the audio. Like it's a sound that you'll recognise if you do any audio production. I've only tried putting square wave signals into these. I'm actually kind of interested to see what would happen with just standard audio, because I think it would kind of wave shape it to a square, which I guess is the same as reducing it to like 1-bit audio, because it'll just be, you've just got one value, it's high or low, so it'll bit crush it down to 1 bit, and then and then it'll you can reduce the sample rate as well, so you can use it as a kind of really basic kind of, degrade effect with some bit crushing and sample rate reduction, or it's just a kind of instrument in its own right. And that's one of my kind of design goals, was to have stuff that you could use on its own, or patch stuff in. So just very quickly, give this some power. So again, the LED is there to give a representation of what the output's doing. See, I don't know if you'll you can kind of see it flickering, so you have an idea of what's happening. So I'm just gonna put that in there. Turn this around. So if I clock it up, if it goes too high, it becomes inaudible. As I change the pitch of the various oscillators, you can kind of hear them. If I get one of my dual oscillators and patch the output of that into the input of one of these, you can kind of hear it. Although not very well, admittedly. Then what I discovered you can do is, if I just patch these inputs in but don't actually plug them into anything, so that kind of defeats the oscillators. What's going on here? Again, you can get some kind of fairly interesting tones out of that. And if you just ground some of them, it can sound kind of interesting. This one doesn't actually sound as good as some of the others. I have had some interesting tones out of that. So that is that one. Oh, that's my last thing about that one is that when I designed it, I had planned to have these capacitors bend over the other way. I didn't quite leave enough room, so I'd probably need to change that so that either they're mounted here and bend over that way, or they're over here but have enough room, because hanging over the edge like that isn't okay. Also, this row needs to be further away from this row. There's not enough room really when you're getting in, especially once you've got knobs on them. There's not enough room to get in there and control them. But that's fine, I'll change it for the next one. Right, so I'm going to immediately break what I stated was one of my design goals. This is an 8-step sequencer. So this is based on, it's got a 4016 just as a clock, and it's a 4017 counter. That's kind of the brain of it. So it's nice and straightforward. There's 8 pots, 8 LEDs, there for your 8 steps. This switch controls, it basically defeats the steps, so it will stay on the current step. This is the clock speed for the steps. That's an input for the clock that overrides this, and there's the output. Now, the first annoying thing about this that I've screwed up is if you plug it in, nothing happens. So it only actually outputs anything if you've got it plugged, like patched into something it can output to. So what I'm going to do is I've got one of my single oscillator boards. I've got too many things in my hands. Try and get some power to this. So I'm just going to plug the output of this sequencer into the pitch control input of this oscillator. And lo and behold, absolutely nothing has happened. I might have just got a dud power connection. No, I haven't. I'm being an idiot. It would help if I actually used the output instead of the clock input. And it would help if I used... Oh yeah, no, that's okay, that's fine, that's what I want. So, there we go. Okay, cool. So, let's see, where are we? Tilt it up a bit, so you can see it's just running through the steps. The brightness of the LED is kind of telling you what the output of that step is. At very low levels, the LEDs just kind of flash a bit, which I don't think they should be doing. So I need to check that out. But it's fine. You can kind of see what's happening. So I'm going to plug the output into this oscillator. So, you know, it's a sequencer. It's pretty rudimentary. I'm still nailing down exactly where the useful range of values are. Because, so if I... Well, I'll stick it on that one. Like, it probably doesn't need to go that low. Because let's face it, that's probably the lowest it needs to be, which doesn't give you a lot to work with. So these are 1 meg pots. I've already done one. This is actually the second one that I built, because the first one that I built, I had it spec'd for 10k pots and it just wasn't enough. And I've gone to 1 meg pots, but this is too much. I maybe want to half that. Maybe want to put 500k pots on there. Or at the minute they're set up as variable resistors, like I've actually maybe need to do it as a voltage divider instead. So yeah, I mean, not much more to say. It'll go very fast indeed. Oh, using the clock input is kind of neat. Let's see if I can accidentally get something cool immediately. So I'm going to use that shift register synth. Nah, it's a bit too fast. I've had good things happen using the noise bastard. Yeah, using the noise bastard as a clock source is pretty cool because that does a lot of interesting pulsating kind of noises, which translates quite well as a clock source. It's quite cool to see. You can see the pitch, kind of pitch changes reflected in this LED. So yeah, that's it. I mean, this is one that I think needs work, definitely could do with another revision. I maybe need to experiment with some different values of potentiometers, but I already ended up having to do a second order of pots, and I am not ready to spend money on a third. 4x1 kind of signal combiner. I'm not going to say mixer because it doesn't have individual controls for these, and I really need to do one that does. I think the second revision will have controls. Also, I think I've got the. I think the pot needs to, like the master volume, needs to be before. I've got this op amp as a buffer amplifier. I think I maybe need to try having that after this pot because it does weird stuff. Also, I need to use one of these that is rail to rail, which this is an LM358. Which is not rail to rail. So I think there's a noticeable drop in volume when you use it. This is kind of a master output. So you know it does the job, but it's needs attention. It's functional, and with the next lot of boards I'll do something better. But it kind of serves a purpose. This thing has been a pain in my ass This is a delay based on a PT2399. There it is, which is a kind of delay IC. And this circuit is straight out of the datasheet for that chip, because this is just the delay circuit that they recommend, not recommend, that they provide, because I thought I'd do that first and then I can mess around with my own version. This took me 2 goes to get right. There's the one that didn't work. And I could not figure it out. I think I learned quite a lot about troubleshooting, trying to get it to work, and getting the multimeter on it and following things through, figuring out compared to the schematic and the board layout kind of diagram whether things are right or not. I had these capacitors over here that are a different colour. Originally they were like this, they were kind of square, because that's what I ended up buying for some reason. So at first I thought maybe it's them, maybe I bought the wrong thing, but replacing them didn't help. Then I thought maybe it was these being the wrong value, or resistors being the wrong value. So on this one I ended up desoldering the pots, trying different pots, and I think the conclusion I came to is that the chip must just not have been working. Look, I kind of got part way through removing some resistors and then gave up. This one, put it together and it just worked. So there you go. Like I spent so much time trying to avoid putting another one together, but in the end, that's exactly what I needed to do. So yeah. So this has got I've lost my little piece of wire that I was using as a pointing implement. There's another one. So we've got input output, feedback, delay time. We've got a voltage regulator in the middle. This chip needs a maximum of 5 volts and everything else runs on 9, so that's a 5-volt regulator. I'm quite chuffed with that. I never used one of those before, but I just did what it said in the documentation and it worked. And yeah, that's kind of it. The things that I want to do with it, I want to add some kind of voltage control for delay time and feedback. I think that's perfectly doable. And I want to maybe experiment with some different value resistors and capacitors to get some different kind of upper and lower possible values, and also put a power LED on it, because let's face it, everything should have an LED on it. So I can plug it in without any input first. Maybe I can't. Let's see if it's going to work. Oh no, you know what, I've just gone and done. Possibly made a terrible error there. Nope, didn't kill it. I plugged my power in backwards. Oops. So this is a kind of quirk of this chip. I should turn this around so you can see it. Like, a quirk of the chip is when you change the delay time, you get those kinds of noises. The feedback will go high enough that it'll kind of infinitely feedback, which is kind of cool. So I'm pretty sure I could get faster delay times out of it just by messing with some other values. Let's plug something into it. Not all the way around. There we go. So, you know, it's a delay. It does delay stuff. That's not the bad one. So yeah, not much more to say about that. I found when I was doing live shows with some of my other gadgets that I was having to use like a guitar multi-effects pedal to add delay, because everything sounds better with delay. So I figured I should just have delay as part of this setup. I'm gonna leave that module over there, because the last thing is I've got a low pass filter. So this was a nightmare to get working. Turns out that those two little diddy capacitors there that say 470 picofarad on them, I've actually got the right value on the board. I'd written it down on my bill of materials as 470 nanofarad, which are like, hang on, I had one on the desk and it's gone. Oh well, they're massive. Here it is. So basically I thought it was that size, so I didn't have enough room, and then it didn't work, and it took quite a while to figure it out, and I felt like an absolute idiot when I realised. The other thing about this is I think, again, because I've used an op amp that isn't rail to rail, I think it kind of acts strangely. It overdrives very easily, and when it's overdriven it doesn't filter particularly well. So you can probably hear it filtering if I just hold the end of this cable. Nope. Okay. Oh well. I'll just plug it into something. So there's a bit of filter in there, but not a lot, and certainly, like, that's resonances at the top, certainly not a lot of resonance there. So this is where, out of all of these things, this is the one that was kind of the biggest faff to get working. So what I discovered, I'm just going to cut to the chase, what I have to do is plug into one of my little 4x1 combiners, plug that into this little passive board that I did, that is basically just a pair of these, they're just connected to each other by a little capacitor, just so it'll only allow DC through, and then from there go into the filter and set the output of the mixer very, very low, like almost to nothing, so as to not overload it. I think in the next revision I just need to set the filter to have a capacitor on the input, so it's only allowing DC, because I'm only using DC. That should... It's apparently not going to work now. Oh, that's good. That's very helpful. Now why isn't it working? Oh, because I've not given any power to the mixer. Good. Good to see that I'm totally with it. There we go. So if I turn that kind of down. And then we'll be able to hear and then as I turn up the output from the mixer, I mean, it sounds kind of cool, but you start to lose a lot of the resonance. There we go. Once we're past about halfway. So, I mean, so that's my best. So like I say, I figured out how to fix it. I'll be honest with you, I don't entirely understand why it's happened, but it's fine. I can work around it, and I'll hope to work towards having a future revision that doesn't require that messing around to make it work. Yeah, that's it. That's all the modules that I've done this time around. Yeah.